By 1943, the strategic situation for the Third Reich was becoming increasingly threatening. The defeat at Stalingrad, the disaster in North Africa, the massive bombings of German cities, all pointed to the inevitable collapse of Nazi Germany. It was at this moment of despair that Joseph Goebbels first publicly spoke of a Wunderwaffe, a wonder weapon, capable of fundamentally changing the course of the war. In secret laboratories and underground workshops, German scientists and engineers worked on projects that seemed fantastic even by 20th century standards. Ballistic missiles capable of striking targets hundreds of kilometers away, jet fighters flying twice as fast as piston-engine aircraft, exotic weapons based on new physical principles. Hitler personally oversaw many of these developments, placing his last hopes on them. For the Führer and his inner circle, the Wunderwaffe became not just a weapon, but an almost mystical symbol, the last chance to save the crumbling thousand-year Reich. The history of the V-2 ballistic missile begins long before the war, in 1930, when young German engineer Wernher von Braun joined the Society for Space Travel. This organization of rocket enthusiasts conducted experiments at an abandoned artillery range near Berlin. At the time, no one could have imagined that their research would lead to the creation of a weapon that would forever change perceptions of warfare. Soon, the talented engineer attracted the attention of the military. In 1932, the Reichswehr, circumventing the restrictions of the Treaty of Versailles, began funding rocket research. By 1937, a secret research center, Peenemünde, had been established on the Baltic coast, a true city of science, hidden from prying eyes. Here, von Braun and his team worked on a series of A-series rockets, culminating in the A4, the future V2. The name V came from the German word Vergeltungswaffe, retaliation weapon. This is how Hitler and Goebbels emphasized the retaliatory nature of the strikes against Great Britain for the bombing of German cities. The technical difficulties faced by the creators of the world's first ballistic missile seemed insurmountable. It was necessary to develop a liquid-fueled rocket engine of unprecedented power, create a guidance system capable of keeping the missile on course, and solve the problem of thermal protection during re-entry into the atmosphere. Every launch of early prototypes ended in an explosion or uncontrolled flight. However, von Braun was not only a brilliant engineer but also a talented organizer. By 1942, his team had succeeded. The A4 rocket made its first successful flight, reaching an altitude of 80 kilometers and covering a distance of 190 kilometers. Hitler, initially skeptical of the rocket program, was impressed. He ordered the mass production of the new weapon. But here, the Nazi regime faced the problem of a labor shortage. The decision made by the Reich leadership became one of the darkest pages in the history of technology. Concentration camp prisoners were used to produce the retaliation weapon. In the underground tunnels of the Kohnstein Mountain, protected from Allied bombing, the underground factory Mittelwerk was established. Thousands of prisoners in inhumane conditions assembled rockets, subjected to brutal treatment by SS guards. According to various estimates, more people died during the production of the V2 than from its combat deployment. Von Braun himself later claimed to have had no involvement in the use of forced labor, but documents and eyewitness testimonies suggest otherwise. The genius of rocketry chose to turn a blind eye to human suffering, focusing on the technical aspects of his creation. On September 8, 1944, the first V2 combat rocket struck London. A thunderous explosion shook the Chiswick district, leaving behind a massive crater and ruined buildings. The British initially believed it was a gas pipeline explosion. So unusual was the nature of the destruction. But soon new strikes followed, and the reality became clear. Germany had deployed a weapon unprecedented in world history. Unlike the V-1 flying bombs, which flew at low altitudes and could be shot down by anti-aircraft guns or fighters, the V-2 was virtually invulnerable. The rocket ascended to an altitude of up to 90 kilometers and fell on its target at 5 times the speed of sound. No air defense systems of that time could intercept it. The only warning sign was a double sonic boom, when first the roar of the explosion arrived, followed by the sound of the rocket's supersonic flight. The German command placed enormous hopes on the new weapon. Goebbels, in his propaganda speeches, promised that the V-2 would bring England to its knees. Hitler was convinced that massive missile strikes would undermine British morale and force them to sue for peace. Reality proved different. Over 7 months of combat use, approximately 3,500 rockets were launched against targets in Great Britain, Belgium, and France. Of these, about 1,150 struck London, and another approximately 1,600 struck the port of Antwerp, which became a key supply point for Allied forces after its liberation. The accuracy of the V-2 left much to be desired. The circular error probable was several kilometers, making the rocket effective only against large urban agglomerations. Because of this, the V-2 became not so much a military weapon as a terror weapon, aimed against the civilian population. About 7,000 people became victims of the rocket attacks, and another 20,000 were wounded. Most of the deceased were civilians. Each rocket, on average, killed 2 people, a disproportionately small result for a weapon on whose development and production colossal resources were spent. The Allies could not counter the rockets themselves, but quickly found another solution. Massive bombing raids on production centers and launch sites became the primary means of combating the vengeance weapon. Operation Hydra, a raid on the research center in Peenemünde in August 1943, proved particularly effective, setting back the V-2 program by several months. In response, the Germans adopted mobile tactics. Special units transported rockets and necessary equipment on tractors, set up a position, launched, and quickly changed locations. This made it difficult to detect and destroy the launchers, but could not compensate for the main problem: a catastrophic shortage of rockets. By the spring of 1945, the V-2 program had virtually run out of steam. The Allied offensive deprived the Germans of their last launch sites within striking distance of London, and rocket production was paralyzed by a shortage of materials and the destruction of transport infrastructure. The last strike on London was delivered on March 27, 1945. In the autumn of 1944, something appeared in the skies over Europe that made seasoned Allied pilots doubt their own eyes. A silver arrow streaked past bombers with such speed that gunners didn't even have time to aim their weapons. This was the Messerschmitt Me-262, "0,1", the world's first jet fighter to enter service. The history of this revolutionary aircraft began even before the war. In 1938, German aircraft designer Willy Messerschmitt received a technical specification for the development of a new generation fighter. Simultaneously, BMW was working on a turbojet engine capable of developing thrust unattainable for piston engines. The first prototype of the Me-262 took to the air in April 1941, but then, still with a piston engine, the jets weren't ready. Only 6 months later did the aircraft make a flight with 2 Jumo 4 turbojet engines. Pilot Fritz Wendel was amazed. The machine accelerated to 850 kilometers per hour, which was 200 kilometers faster than the best fighters of that time. However, Almost 3 years passed from the first flight to serial production. German engineers encountered many technical problems. The engines overheated, quickly exhausted their resources, and required scarce materials. Particularly critical was the shortage of heat-resistant alloys containing nickel and chromium, strategic metals that were virtually non-existent in Germany. A fatal role in the fate of the Me-262 was played by Hitler himself. Upon seeing the prototype in 1943, the Führer asked a question that doomed the project to semi-success. Quote, 2. Receiving an affirmative answer, Hitler ordered the reorientation of production towards creating high-speed bombers instead of fighters. This decision was a catastrophic miscalculation. The jet fighter, capable of intercepting Allied bomber armadas, turned into a mediocre bomber. Precious time was lost. Only in the autumn of 1944, when the strategic situation became critical, did Hitler finally allow the Me-262 to be used as a fighter. By this time, the Allies already dominated the air. Nevertheless, the Quote 3 struck terror into bomber crews. Armed with 4 30mm cannons, it could attack at speeds unattainable for piston escort fighters. American pilots nicknamed it the Quote 4. In parallel with the Quote 5, the Germans were developing other jet aircraft. The Heinkel Ichi 162, a light fighter created as part of the program. It was to be built from wood and other non-metallic materials by unskilled workers and teenagers. Another breakthrough was the Arado AR-234, the world's first jet bomber reconnaissance aircraft. But it was already too late. Despite technological superiority, jet aviation could not change the course of the war. There was a shortage of fuel, spare parts, and trained pilots. The Allies systematically bombed airfields and factories. Out of the 1,500 Me-262 built, no more than 300 machines were able to participate in combat operations. In the last months of the war, German jet aircraft became invaluable trophies for the Allies. Soviet, American, and British specialists literally hunted for them, understanding that these machines were the future of aviation. The technological revolution, initiated in Germany, continued in the post-war world, forever changing the face of military aviation. Beyond the weapons that were realized and deployed in combat, engineers of the Third Reich developed projects so ambitious that they seemed to come straight out of science fiction novels. In secret laboratories, blueprints were created for machines capable, in the opinion of their creators, not just of turning the tide of the war, but of securing global dominance for Germany for decades to come. One of the most grandiose projects was the intercontinental missile A9/A10, also known as the America missile. This two-stage monster was intended to deliver warheads across the Atlantic Ocean directly to New York and Washington. The first stage, A10, was a gigantic rocket the height of a 20-story building, which would launch the second stage, a modified V2, into a suborbital trajectory. The range of such a system exceeded 5,000 kilometers. Even more fantastic was the Sonnengewehr, Sun Gun project. This was a concept for an orbital battle station equipped with a giant mirror hundreds of meters in diameter. The idea was that the mirror would focus sunlight onto the Earth's surface, incinerating enemy cities like a gigantic magnifying glass. Nazi scientists even conducted preliminary calculations showing the theoretical possibility of such a weapon. Armored vehicle designers were not far behind. On drawing boards, projects for super-heavy tanks were born, in comparison to which even the King Tiger seemed a light machine. The most famous was the P-1000 Ratte project, a 100-ton monster with 3 turrets and a crew of 20. Even more absurd was the Monster tank, weighing 1,000 tons, which was supposed to move on 3 tracked bogies and carry guns up to 280 millimeters in caliber. Why did these projects remain on paper? There were several reasons. Firstly, a catastrophic shortage of resources. By 1944, Germany was experiencing a deficit in everything, from strategic materials to skilled labor. Even existing armaments programs did not receive the necessary funding, let alone fantastic projects. Secondly, the technological limitations of the era. Many concepts simply were decades ahead of their time. The necessary materials and production technologies for creating intercontinental missiles did not exist. Control systems did not provide the required accuracy. Orbital stations remained beyond the realm of possibility for the astronautics of the 1940s. Thirdly, strategic miscalculations by the leadership. Hitler and his entourage often made decisions based not on technical feasibility, but on propaganda effect. Resources were dispersed among many competing projects instead of concentrating on the most promising directions. The gap between propaganda promises and the real capabilities of German industry became increasingly apparent. Goebbels continued to speak of the imminent appearance of new wonder weapons, capable of changing the course of the war overnight. But time was working against Germany. Each day brought closer the collapse of the Third Reich, and with it, the end of most fantastic projects. By mid-1944, the Soviet leadership had a fairly complete understanding of German technological breakthroughs. Sources of information included both intelligence data and the first captured samples of wonder weapons. Stalin, who received regular reports on the new developments of the Third Reich, quickly recognized their potential threat and their promise for the post-war development of the Soviet armed forces. The first fragments of a V-2 rocket fell into the hands of Soviet specialists in July 1944, when one of the rockets crashed on the territory of Poland, liberated by the Red Army. Upon examining the fragments, Soviet engineers were amazed by the technological level of the German design. By order of the State Defense Committee, a special commission was created under the leadership of Lieutenant General Lev Gaidukov to study captured rocket technology. In parallel, special technical groups were formed, which were to follow directly behind the advancing units of the Red Army. Their task was to find and preserve German documentation, equipment samples, and, most importantly, specialists who worked on secret projects. These groups were staffed by the best engineers and scientists, many of whom were recalled from the front. Of particular value to the Soviet side was information about German jet aviation, when, in early 1945, the first samples of the Messerschmitt Me-262 fell into the hands of Soviet troops. They were immediately sent to Moscow for detailed study. Chief aircraft engine designer Alexander Mikulin and aircraft designers Artem Mikoyan and Alexander Yakovlev were tasked with mastering jet engine technology as quickly as possible and creating their own samples of jet aircraft. Stalin personally supervised the process of studying German technologies. According to the memoirs of Marshal Zhukov, at one of the meetings in the Kremlin in February 1945, the Supreme Commander-in-Chief stated, "The war will soon end, but a new war will begin, a war of technologies, and we must be ready for it." These words defined the strategy of the USSR in the last months of the war and in the post-war period. In March 1945, a special group, Nordhausen, was created under the leadership of General Nikolai Petrov. Its goal was to capture the rocket center in the German city of the same name, where V-2s were produced. The group included specialists of various profiles, from rocket engineers to chemists specializing in rocket fuel. Among them was the future chief designer of the Soviet space program, Sergei Korolev, recently released from imprisonment and rehabilitated. When Soviet troops occupied the territory of the rocket center, they found that most of the equipment and documentation had already been evacuated by the Germans or captured by the Americans. However, even what was found was of enormous value. Dozens of unfinished rockets, drawings, and technological equipment were discovered in the underground tunnels of Mittelwerk. In the last weeks of the war, the priorities of the Soviet command changed. If earlier the main task was the fastest possible advance to Berlin, now the capture of scientific and industrial centers of Germany became no less important. Special units received accurate maps indicating objects of technological interest. Often these objects were taken under guard immediately after capture to prevent looting and destruction of valuable equipment. On May 5, 1945, when Berlin had already been captured by Soviet troops, a meeting was held in Podlipki, near Moscow, attended by the 38-year-old engineer Sergei Pavlovich Korolev, who had been released from imprisonment. This very day can be considered the beginning of the Soviet rocket program, which was destined to change the balance of power in the world and pave humanity's way to space. Korolev was appointed to a technical commission that was to go to Germany to study German rocket technologies. Despite years spent in camps and sharashkas, he retained his engineering talent and incredible energy. Now he was to lead the work on mastering Wernher von Braun's legacy. In July 1945, a large-scale operation, Aviation, began to transport German rocket specialists and equipment to the USSR. While the Americans, as part of Operation Paperclip, took von Braun and key V-2 developers, Soviet specialists focused on mid-level technical personnel and production equipment. More than 2,000 German engineers and technicians, along with their families, were moved to the Soviet Union. In the city of Nordhausen, where V-2 production was located, Soviet specialists, under the leadership of Korolev and General Gaidukov, assembled several dozen rockets from the remaining parts. But the most valuable trophy was the technical documentation and the knowledge of German specialists who agreed to work for the USSR. In Germany, in the Soviet occupation zone, the Nordhausen Institute was created, where, under the guidance of Soviet engineers, German specialists restored rocket production technology. Korolev spent most of his time there, meticulously studying every detail of the German rocket. In the autumn of 1946, the first test launches of the V-2s assembled in Germany took place in the area of Lake Seeliger. The results were disappointing. Most of the rockets deviated from course or disintegrated in flight. It became clear that simple copying was not enough. A deep understanding of all technological processes was needed. In August 1946, a decision was made to create in the USSR its own production of ballistic missiles. Korolev was appointed chief designer of the first Soviet ballistic missile R-1, practically an exact copy of the V-2. A colossal work began to reproduce German technologies at Soviet enterprises. The task proved incredibly difficult. It was required not just to copy the design, but to recreate hundreds of technological processes, many of which were unique. Soviet industry did not produce the necessary alloys. There was no equipment of the required precision, and there was a lack of experience in creating complex control systems. Korolev proved himself not only as a brilliant engineer, but also as a talented organizer. He coordinated the work of dozens of enterprises throughout the Soviet Union, personally solved emerging problems, fought bureaucracy and the skepticism of some military leaders who did not believe in the prospects of missile weapons. In October 1947, The first successful launch of the R-1 missile took place at the Kapustin Yar test site. This was a triumph of Soviet science and industry, proving that the USSR was capable of independently creating the most complex technical systems. But Korolev understood that simply copying German developments was a dead end. Already during the reproduction of the R-1, he began work on his own more advanced designs. Thus was born the R-2 missile, which, with similar dimensions, had twice the flight range. It was followed by the R-5, the world's first intercontinental ballistic missile capable of delivering a nuclear warhead to another continent. Less and less of the German legacy remained in these designs. Soviet engineers developed their own engines using new types of fuel, created more advanced control systems, and solved the problem of thermal protection during re-entry into the atmosphere. Especially important was the use of separable warheads, which significantly increased the flight range. Thus, based on captured technologies, an independent Soviet school of rocketry was born, which soon took a leading position in the world. On October 4, 1957, the R-7 launch vehicle, created under Korolev's leadership, launched the first artificial Earth satellite into orbit, opening the space age in human history. As early as the mid-1930s, Soviet aircraft designers began to consider the creation of aircraft with fundamentally new types of engines. In 1936, engineer Arkhip Lyulka presented the design for the first domestic turbojet engine, the RD-1. However, at the time, this idea seemed too revolutionary, and the war that soon began forced a focus on improving already mastered piston engines. A real breakthrough in Soviet jet aircraft construction occurred only after the victory over Germany. In May 1945, a special technical commission led by General Ivan Petrov was tasked with finding and studying all samples of German jet technology. Of particular value were the Jumo 004 and BMW 003 engines, which were installed on the Me-262. Dozens of captured engines were delivered to the Central Institute of Aviation Motors in the Moscow region. Soviet engineers literally disassembled them screw by screw, studying every detail. Simultaneously, work continued in the USSR on its own jet engines under the leadership of Lyulka, Klimov, and Mikulin. In August 1945, Stalin summoned aircraft designers Artyom Mikoyan, Alexander Yakovlev, and Semyon Lavochkin. The task was set extremely clearly: to create a Soviet jet fighter in the shortest possible time that would not be inferior to the best foreign models. At the same time, Stalin emphasized, "We need not just an airplane with a German engine, but our own Soviet machine, which will become the basis for future developments." A real competition unfolded between the design bureaus. Mikoyan and his deputy, Mikhail Gurevich, worked on the I-300 aircraft, the future MiG-9. Yakovlev created the Yak-15 based on his successful piston fighter, the Yak-3. Lavochkin designed a completely new machine, the LA-150. Mikoyan's OKB chose the path of creating a fundamentally new design. The MiG-9 had a classic layout with two RD-20 engines located in the fuselage. These engines were Soviet copies of the German BMW 003, refined under the leadership of Vladimir Klimov. The fighter's armament consisted of one 37mm and two 23mm cannons, a powerful argument in aerial combat. Yakovlev chose a more conservative but also faster path. He took the fuselage of the well-mastered Yak-3, removed the piston engine, and installed a captured Jumo 004 in its place. The resulting aircraft, the Yak-15, was simpler and lighter than the MiG-9, but had lower speed and flight range. The first flight of the MiG-9 took place on April 24, 1946. Test pilot Alexei Grinchik was at the controls. Just a few hours later, the Yak-15 also took to the air, piloted by Mikhail Ivanov. This coincidence was not accidental. Stalin ordered the tests to be conducted on the same day to determine the winner in the unofficial competition. Both aircraft demonstrated worthy characteristics, and it was decided to launch both machines into serial production. The MiG-9 as the main frontline fighter with greater range and firepower, and the Yak-15 as a simpler and cheaper-to-produce aircraft for air defense and training purposes. The first production MiG-9s and Yak-15s entered service in early 1947. For Soviet pilots, accustomed to piston aircraft, the transition to jet technology was not easy. The new machines required different piloting skills and behaved differently during takeoff and landing. Special training centers were created to master jet fighters. Despite all their achievements, the first Soviet jet aircraft had serious drawbacks. The engines had a short service life, only 50 to 70 hours, and low reliability. The aircraft had insufficient maneuverability for jet machines. But most importantly, they were already lagging behind the latest American and British models, such as the F-84 Thunderjet and Meteor. Therefore, simultaneously with the production of the first jet fighters, intensive work was underway on second-generation aircraft. In 1947, the Mikoyan OKB began designing the MiG-15, a fighter with a swept wing and a more powerful engine. This aircraft, adopted for service in 1949, was no longer inferior to the best Western counterparts and provided worthy competition to American fighters in the skies of Korea. By 1950, it became clear that simply copying German technology no longer met the strategic interests of the Soviet Union. A turning point had arrived, when domestic designers had to not just master captured developments, but surpass them, creating fundamentally new weapon systems. In rocketry, this transition was marked by the appearance of the R-3 missile, the first Soviet ballistic missile using storable fuel components. While the R-1 and R-2, despite all their improvements, still carried the genetic code of the V-2, the R-3 became a completely original design. Korolev and his team abandoned alcohol and liquid oxygen in favor of nitric acid and kerosene, which allowed the fueled missile to be kept combat-ready for weeks, not hours. Concurrently, a similar breakthrough occurred in aviation. The MiG-15, with its swept wing and all-metal construction, no longer had anything in common with German prototypes. Moreover, when Soviet MiGs encountered American F-86 Sabres in the skies of Korea, they demonstrated equal, and in some parameters, superior characteristics. It is noteworthy that both the Americans and the Soviets started from the same technological base, captured German developments. Operation Paperclip, conducted by the Americans in April-May 1945, allowed over 1,600 German scientists and engineers, including Wernher von Braun himself, to be brought to the USA. Meanwhile, the Soviet operation Osoaviakim was conducted later and involved fewer key specialists. However, the results of this trophy start proved unexpected. The Americans, who received the best German specialists, for a long time followed the path of direct development of German ideas. Their first ballistic missile, the Redstone, was a direct descendant of the V-2. At the same time, Soviet designers, forced to rely more on their own strengths, more quickly transitioned to creating original designs. This competition reached a new level in the early 1950s, when both superpowers began developing thermonuclear weapons and their delivery systems. Korolev started work on the R-7, the world's first intercontinental ballistic missile. The Americans were developing their Atlas. The race was literally down to months. In the field of jet aviation, the competition was no less fierce. The experience of the Korean War showed that jet fighters had become the decisive force in aerial battles. Both sides rapidly developed aircraft capable of breaking the sound barrier. The MiG-19 and the American F-100 became the first mass-produced supersonic fighters of their respective countries. It is noteworthy that a key role in Soviet developments was played by designers who did not have direct access to German specialists, but who managed to creatively reinterpret captured technologies. Korolev, Mikoyan, Tupolev, Yakovlev created their own design schools, which soon no longer needed foreign models for copying. By the mid-1950s, the technological competition between the two superpowers had reached a fundamentally new level. It was no longer about developing the German legacy, but about creating next-generation weapons systems. Trophy science had fulfilled its role as a launch pad for a grand technological leap that ultimately led humanity into the space age. The technological breakthrough achieved by German designers during World War II laid the foundation for decades of geopolitical confrontation that shaped the second half of the 20th century. V-2 rockets and Me-2 jet aircraft became not merely weapons of the doomed Third Reich, but also the bedrock of a new world order in which technological superiority meant survival. When the last shots fell silent in Europe in May 1945, a new invisible war began, a war for German technological heritage. Soviet and American specialists literally pieced together documentation, equipment, and, most valuable of all, people, bearers of unique knowledge. Operation Paperclip allowed the Americans to get their hands on Wernher von Braun himself and his closest associates, while the Soviet Operation Osoaviakim provided the USSR with technical personnel and production equipment. The consequences of this hunt for minds proved truly historic. Already on October 4, 1957, a modified R-7 intercontinental ballistic missile, created under the leadership of Sergei Korolev based on studied German technologies, launched the first artificial Earth satellite into orbit. This event came as a true shock to the West and marked the beginning of humanity's space era. The American response was immediate. Wernher von Braun's team accelerated work on their rockets. The space race began, culminating in the human landing on the Moon in 1969. It is notable that the Saturn V launch vehicle, which delivered American astronauts to the Moon, was created under the leadership of the very same von Braun who, 25 years prior, had developed the V-2 for bombing London. In the field of jet aviation, development progressed no less rapidly. From the first MiG-9 and Yak-15, Soviet aviation evolved to supersonic MiG-21 and Su-7 fighters, which became symbols of the Cold War. The Americans, starting with the adaptation of German technologies, created an entire line of combat aircraft, from the F-86 Sabre to the F-4 Phantom. Air battles in the skies of Korea and Vietnam became the first proving ground where the heirs of the German jet revolution clashed. However, the technological race also had a dark side. It led to the creation of weapons of unprecedented destructive power. Intercontinental ballistic missiles with nuclear warheads, capable of reaching any point on the planet in a matter of minutes, became the main argument in geopolitical disputes. The doctrine of mutually assured destruction, based on the capabilities of these weapons, kept the world on the brink of global catastrophe for decades. A natural question arises. Was it ethical to use technologies created by the Nazi regime, which brought so much suffering to humanity? This question tormented many scientists and politicians for decades. The Americans, in taking von Braun and other German specialists, turned a blind eye to their Nazi past and the use of slave labor in the creation of the V-2. The Soviet Union, although it suffered more than other countries from Nazism, also did not disdain German technologies and specialists. Proponents of a pragmatic approach argued that technologies themselves are neutral, and their application depends on the intentions of people. Opponents pointed out that technology cannot be separated from its creators and the circumstances of its creation. This ethical dilemma has no unambiguous solution and remains relevant to this day. What did the German Wunderweapons bring to humanity in the long run? On the one hand, a constant threat of self-annihilation in nuclear war, an arms race that consumed colossal resources. On the other, a breakthrough into space, the development of peaceful technologies, from satellite communication to nuclear energy. The paradox of history is that weapons created for destruction ultimately paved the way to the stars. Technologies developed in the last years of the doomed Nazi regime determined the development of humanity for decades to come, becoming both the greatest threat and the greatest hope for our civilization.